Hey everyone, in this video we are going to explore a deep reinforcement learning agent which learns to play the snake game from scratch. It's currently a training and I have a script which picks up from the latest episode and plays the game automatically so we can see it visually. So we'll let this one train a little longer while I explain how this process works. We will review the code, and the code files also will be available to download at my Patreon. Link will be in the description, but let's get a high-level overview of what's happening. So reinforcement learning is a open-ended tool set, as you can apply this to any problem in which you can write the simulation of the problem. Here, in this case, we have a snake game in which we can define an observation state for our agent, and we can take actions on this problem. So as long as we can actually do that, and we know what the right actions are or should be, then we can design a reward function or reward structure. So as long as we can simulate the problem we have, this problem can be anything that decisions need to be made, right? It's a decision-making process. In this case, the snake is deciding whether to go straight, turn left, or turn right. So those are our actions. Those are our decisions. And then the agent needs to be able to observe a state of the simulation. In this case, for example, if we go back to our state is defined in this get state function. Essentially, the agent receives all this input, such as if the snake is moving up, down, right, left, where the food location is in comparison to its body or head, obstacles in immediate vicinity. There's a total of 26 items we pass on to the agent as a state. So that's his observation state. That is what the agent sees, the neural network sees from this problem simulation. And then once it sees something, then it can take actions such as to continue going forward or turn left or turn right. And then the reward is designed as to tell the agent, well, whether if it had made correct decisions or not, such as when we give a positive reward when it is able to find food and eat it. Here, if we look at this in our code, if the snake gets the food, it receives 10 reward. If it goes around not finding the food for a long time, we give it a negative reward. If it results in a collision with itself or with the wall, then we give a negative reward. And if it's every step it takes without reaching the food, we give a small negative reward so that the model actually can learn from this feedback. And then after all this is done, then we get the next state, which is the next observation state in reinforcement learning. This is actually talked about as SARS state. You get the state, you take actions, you let the network take actions on it. You perform a reward function so that the model can learn. You give it feedback, and then you get the next state. And we have an agent here, which receives the observation, then returns actions. We implement those actions in our simulation, and then we get the rewards based on what the action resulted in, and we send this back to the agent, and then that's how it's going to work. So there are some obviously moving parts in this, such as like some configurations to this agent. There are some configurations related to the agent itself and some to the neural network that does the processing. There's a so-called gamma, which is a discount factor, which tells the agent how much it values the immediate rewards it's going to receive versus future rewards. That's why it's called a discount factor. Usually it's set to something like 0.99. If it's set to 1, that means the agent will only care about future rewards. And if it's set to 0, then it'll only care about immediate rewards. There's also what's called an epsilon, which is actually the random actions that the agent takes. So we forcefully we let the agent take random actions sometimes. This is called an exploration versus exploitation strategy. The reason epsilon exists is that the agent can take some random actions and perform exploratory function. Because we are passing the observation state, we are relying that our process will actually cover many of the varieties of the situations that the agent may find itself in. And epsilon kind of guarantees that actually the agent takes some random actions and explore new information. And exploitation is when agent is actually relying more on what it has learned and actually acting. The neural network is driving the agent. Usually epsilon is set to a high number, like such as 1. which means the agent starts by making random decisions at first, and then we slowly reduce it using what's called an epsilon decay. And eventually, the agent will perform more and more actions based on what it has learned. And this is what that means. And I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects as a patron. You will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses. And my most recent and most proud one, the 1000x MasterClass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well. And then, of course, we have a network shape, which is the shape of our neural network. How many layers we have, how many nodes we have. Batch size is how many experience of this type that the agent accumulates before actually trains itself. So it happens in steps. Something like it performs 1,000 of these combinations, then we train the agent, for example. That's what's called a batch size. And then the learning rate is related to how within the mathematical operations, so-called gradient descent, how fast that process is moving. So these are all crucial. And we will actually explore several different examples with different states. We will explore all the code, of course, but like I said, the code files will be available at my Patreon. I also built a simple hyperparameter optimizer, which uses grid search to test different learning rate values, different batch sizes, and different gamma values. These are by no means the only things we should check for, but this is just to show you that hyperparameter can get complex. And unless you have a very good intuition, even when you have a very good intuition, you have to perform search to find, okay, what is the best number for the gamma, for example? What is the best epsilon decay? What is the best network shape that applies to this problem? And things like that. That's called hyperparameter search. So we're going to explore that as well. And so before we begin reviewing the code, let's see where we are at within our training. So currently we have performed 20,000 episodes, meaning the agent played 20,000 games, and it's averaging about roughly 17 in the previous 1,000 games that it has played. We can also see the rewards that the agent has accumulated right here. And you can see that our epsilon has been steadily decreasing, and it settles on 0.01. We still give agent a small chance to take random actions to encourage exploration. But I've done this many times before. With this configuration, it kind of tapers off around 17. So let's take a look. So this is how it plays currently. You can achieve up to, I believe, 45, score of 45. Oh, here it actually achieved 52. So it plays pretty well. It's by no means perfect, but I'll let you watch a few games and I will start reviewing the code. And you can see the scores here on the side after each game. Wow, it did really well at that time. It got a score of 48. So as you can see, it's learning and it's doing very well, but the performance tapers off at some point. So this is where it gets interesting, where you have a lot of moving parts you can tune. This is a fun process, but let's begin by reviewing the code now. Okay, let's start by reviewing the code for the agent. But before we do that, I do want to mention that if you look at the average scores across episodes, the agent was scoring very low. And towards the end, agent is scoring now very high, meaning the learning process is now more give or take complete. You never know what will happen if you keep running it, but as you can see, our epsilon was reducing too, meaning in the beginning, the agent was taking more random decisions. And at the end, we settled on a very low epsilon value, allowing the agent to explore even at later stages of the training. So the requirements for this is PyTorch, pretty much, but I'm not going to have a requirements.txt file, or actually I'll create one, but essentially I will point to this page on how to install PyTorch. If you go to this page, you can select your options, whether you're on Windows or Mac or Linux. And once you select your options, then it'll give you a pip install option, and you can run this and install PyTorch. Now, if you have a GPU or if you're running on Mac, I believe it automatically uses the Mac GPUs. or you can select CPU as well, this script. Anyway, just after you run this, you should be good to go. This script automatically detects whether you have a GPU or not if you installed that configuration. Otherwise, it runs it on your CPU. There's nothing wrong with running it on CPU. It's just it will be slower. You can also use Google Colab too. Yesterday, I was testing some different state settings and I was using an A100, for example. So keep that in mind. So here we're defining the game grid 20 by 20. Here we are checking to use GPU or not. And here we defined the game. This is our problem domain. This is our simulation. In this case, we are defining a snake game. So this is pretty much a simple snake game. We are not actually rendering the snake game, but we are actually running it. And then we define the snake NN, the snake neural network. And here we are defining our layers. We are using linear layers. We are not using convolutional layers, but you can also use that as well. I may make another video on that. So our input size has to match the state. Here I'm saying this needs to match the original model layers if continuing training from a checkpoint also, because this can also pick up from a checkpoint that you've saved. Like here, this is our latest 25,000 checkpoint. The input to the neural network has to match the size of the state. So here we are defining our state, and if we were to count all these inputs, then it'll amount to 26, and that is the first layer of our neural network. That is our input, the state, and then the rest of it is our dense networks. For example, this is the first layer. Second layer is 64, 128 neurons, 64, and our output is 4, meaning 4 actions. And then this is the forward pass of the network. So this is our network defined. If you change the state, you will probably want to change it too. You can also experiment with different network shapes. And here's the game environment. So the simulation is the environment here in which we are actually going to run the agent. So we pass the snake into the snake game, and actually just pretty much this is how we spawn the tool, and we take a step in using the action that was provided to us. And the snake takes an action, and the snake moves, and then we keep track of the steps without food if the snake hasn't found food. And here, if the snake finds the food, we grow the snake body, and then we reset the steps without food, and we increase the reward by 10. This is arbitrary. Of course, this requires some optimization. Keep that in mind. And then if the steps without food is larger than max steps without food, then we reward a negative 10. This is to encourage snake not to take moves without reaching the uh, food for a long period of time. The max steps without food is 20 by 20, our grid size 400. So if the snake has taken 400 actions without finding the food, we give it a negative reward of 10. If the snake collides with itself or the walls, then we give it a negative 10. We also give a small negative reward for each step that is being taken. So, meaning this is to balance the reward for finding the food. So, to try to make the snake more efficient on wanting to take actions to try to find the food. Here we define our state. So our state is going to be a list of the current direction and the food location relative to the head, obstacles in immediate vicinity, danger detection, and the distance to food normalized. So I'm not going to go into detail of this. Actually, I got Cloud 3.5 Sonnet to write these, but you can actually observe them if you like. Pause the video. This is the length of the snake, steps without food, normalized, tail position relative to the head, and there's some additional information such as available space, neck is up, down, left, right, and then we turn it into a tensor using torch.tensor, and this returns it, and this will be the input to our model at every step of the way. We have a method to save the model, and then we have a method to actually load the model if we are going to continue from a checkpoint, continue training. And our train function is going to check if a checkpoint path has been passed to this function. If so, it's going to load it. Otherwise, it's going to create a new agent, which for whichever device your system is running on, whether a GPU or CPU. And optimizer is is the method in which the neural network is optimized. We are using Adam optimizer, and we pass the model parameters and we set a learning rate. So this is very crucial. Normally speaking, in this script, we are not changing the learning rate. And I found this learning rate with a simple hyperparameter optimization run. I'm not saying this is the best learning rate, but this was performing better. Normally, you want to start with a relatively high learning rate and use a learning rate scheduler to reduce the learning rate over time. You can also do that manually. But for these scripts, we are not using any learning rate scheduler, or we're not changing the learning rate. That's why the file names say no LR schedule. And scalar is grad scalar. I'm not exactly sure what this is, but I believe it may be related to the mixed precision training. I should do more research on it. So our epsilon is 1, meaning when the agent starts running, it will start with making completely random decisions. That is what we were looking at earlier. Remember, our epsilon was high, and then we slowly reduce our epsilon with an epsilon decay, which we will see here, our epsilon decay value. And we initialize the scores and total rewards list, and we create a memory using DQ of Python. So this is going to be the memories of you're going to store the memories of the agent in here, meaning every action that the agent takes, we're going to keep it as a memory, because once we reach this batch size in memory, then this is going to trigger the learning process. The batch size is how many experiences we are accumulating before triggering the next learning session. This is calculated by looking at 2 to the power of some number. For example, 4092 is 2 to the power of 12. You can try different batch sizes, but I found from my hyperparameter optimization that this worked well for me. But normally speaking, the higher this, then the more efficient the training is. And if we actually look at our task manager, my GeForce RTX 4060 is running fully, but we're not doing a lot of VRAM usage, memory usage. If you increase this batch size, that is what goes into the memory. Just remember that. So there's no limit to what batch size you use other than your memory. And of course, depending on what kind of performance you're getting. Gamma is set to 0.99. This again came from the hyperparameter optimization run that I did. Gamma is the discount factor. If this is high, then the model will consider more the future possibility of rewards. And if this is low, then it will be more short-sighted. It will care for more of the rewards that it can obtain right now. The reason why these are important, because if you play around with reinforcement learning agents, they can actually cheat and get stuck in loops, not particularly in Snake. That's why the combination or the dynamism between the reward function and gamma is kind of important. You want to allow the agent proverbially to think more for the futures to maximize its rewards and therefore take better actions. This epsilon decay is a very high value. Every time at each step, we multiply this with this epsilon, effectively reducing it by a very small amount. But when you're running thousands of iterations, that's reducing quite fast. We do set an epsilon minimum. This is again to encourage, even at later stage of the training, that the agent is still taking some random actions and engaging in exploratory behavior. Number of episodes is 500,000. This is how much our full agent training process is going to run. And next steps is 5,000. This is when we will be saving the checkpoints every 5,000 step. Train frequency is 5, train every n episodes. So we check to reach at least every 5 episodes, or whichever both of these factors has to be true. We should have accumulated 16,000 observations, and we have played at least 5 games before we training. Then we pretty much loop over a number of episodes, initiate our game, we get our state, we initialize the total rewards and steps to 0. And while the steps is less than max steps, we take one step, we take one action. Okay. If this random value is less than the epsilon, then we take a random action. Otherwise, we actually get the Q values and then the action from the network itself. And then the game over and the reward is returned to us by the step method that we have looked at based on the action that we have taken. And then our next state is going to be, again, getting the state. and then we apply the reward, and then we append the state action reward next state and the game over conditions to our memory, and then we equal the next state to our current state. And if game over, then we break. Then we append to the scores and append to the total rewards. Now here we are going to perform batch learning. If the episode, if we reach 5 episodes, as we have specified here, train frequency, and the length of memory is larger than the batch size, then we will actually engage in training. So we get a random sample from the memory equaling to the batch size. Then we get the states, action, rewards, and next states from the batch. Then we extract the states by using torch.stack, actions, rewards, and next states, and done. And we apply it to the network. Yeah, with this AutoCast, I believe I did some research on it. It does mixed precision training. I don't know the exact mathematical stuff that's going on with it, but it said that it actually performs better if you perform mixed precision training, and AutoCast does that. You can read more about it. And here we actually run the agent and we calculate the loss. Usually speaking, when you're training neural networks, you want to minimize the loss. Here, I believe here we are using mean square error loss. If you go into this NN function, you'll be able to see that there are many loss functions. And I applied this. I'm not exactly sure, but I think we reset the gradients possibly. These are just steps to update the neural network's situation so it can learn. And then we get a new epsilon. We check if we reach the minimum epsilon, or otherwise we apply the epsilon decay. And we're going to save every 5,000, and we're going to print the status every 1,000 episodes. We're going to print the average score in the last 1,000 episodes and the average total reward and what the epsilon is. That is what we're seeing in the terminal, and we are saving the model every 5,000 episodes actually. So this should actually say N. Yeah, and say we save the model. Here we train. If you want to train from a checkpoint, you can run this method and it should pick up. We are not saving everything that is at that checkpoint, such as that latest state of the training, but this should continue, hopefully. Yeah. So this is it. When you run this, then we engage in training. And as you can see, I'm still continuing to train while I'm recording this video. And you can see that we have actually plateaued around 17. And our snake is continuing to play the game. But at this time, it's really stopped improving. We perform further hyperparameter optimization or something like that. I'll stop this at this point. So next up is we have this best snake.py, meaning this script will automatically pick up the latest episode, latest checkpoint and play from that. Here, that's why we are importing the snake NN and snake game from the file that we were just looking at. If you do experiment and create different conditions, make sure to import from the correct file. And then here we just pretty much get the latest checkpoint by checking these files. And then we load that model and then we render the game. And as we're playing, we are going to check for new checkpoints becoming available. We're going to check every 10 seconds. If we have a checkpoint, we load it. And while true, we're going to check if we find a new checkpoint, such as if 35,000 will become available, we're going to load it. Otherwise, we just play the game. That's about it. And we get our, as you can see, we get our actions directly from the neural network at this point, and that's it. And you can adjust the game speed here, clock.tick. If you increase this, the game will play actually faster. So this is what the best snake is. So previously on the left side, the left terminal, I was running the training, and on the right, I was running this best snake game, which was automatically playing the game based on the latest checkpoint. I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects as a patron. You will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses. and my most recent and most proud one, the 1000x MasterClass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well. Next, let's take a look at the hyperparameter optimizer. So here we are doing much of the same things. We're initializing the device by torch. And we have our snake class, just like we had, and the snake neural network, same as before. And our state is the same. So everything so far is same model, load model. And but here in the train, we specify a list of learning values. As you can see, different values, different batch sizes, and different gamma values. If you remember, the gamma values were the discount factor. And the best average score, best hyperparameters, and we generated all combinations of hyperparameters as a iter_tools.product. We're just going to get a list of all combinations, and then we initialize the results store. Maybe I can run this actually so you can see. Let me just change the number of episodes to 2000 so it'll actually run a bit faster. So when I run this, you'll see that we pick one combination, such as in this case, this learning rate, batch size, and gamma. And we will train for 2000 episodes. We'll take a look at the average scores, and then we'll continue trying to find the best hyperparameters. So this train method actually does the hyperparameter search. Once we get the hyperparameters, we pick a learning rate, batch size, and gamma from hyperparameter combinations. And then we load the model, and then we actually run the training cycle with this. This is the same, except once we perform this, we go back to the beginning and actually pick a new set of learning rate, batch size, and gamma from hyperparameter combinations. So that's what happens. See here, as we are running, we finished the first 1000 episodes and we got 0.77. So we're going to do one more 1000 episodes and then we're going to move on to the next batch, next set of hyperparameters. So this is what it does. The rest of it is the same, except here we are calculating the scores for the hyperparameter combinations. And you see here we are printing the average score and we're storing the results into the results dictionary as the learning rate, batch size, and gamma, which parameters we've used, along with the average score, learning rate, batch size, and gamma. And then if any one of the hyperparameters perform better, then we save that checkpoint as the best model HB search PTH. So we continually check and save the best possible model that we found so far. So this is fine. You can also, this has another function called train with parameters, which will take in a specific learning rate, batch size, and gamma. And at the end of our hyperparameter run, we actually call this with the best hyperparameters with the checkpoint of the best model that we have already found. Because since we are only doing this for 2000 episodes, at the end of hyperparameter search, we will continue from that best model, from that checkpoint, using the best hyperparameters. And train with hyperparameters pretty much is the same training process which we have seen. Yeah, except it takes in the learning rate, batch size, and gamma. But it's the exact same thing as we have seen when we were training with the original file. Now, as this is ongoing, but this is about that. I'm actually going to break out of it. Once this hyperparameter is completed, it'll create a dictionary. It'll run for a while, depending on how many different varieties of hyperparameters you were searching for. It can take a couple hours in some cases, and then it'll save a dictionary of the hyperparameters. And if you look at our print statements, we can see how each learning rate, for example, this particular combination performed in the first 1000 and the second 1000. This next set, for example, didn't perform as well. But you can see the performance of them here, but they will be actually written to the dictionary at the end also. And the best combination will also be printed at the end, the best hyperparameters. So now let's take a look at some different state configurations. For example, when the snake is actually observing a 5x5 grid around its head, and then when the snake is observing a simplified version of the whole board. If you look at this file with 5x5.py, the only difference here is everything else remains the same except our network shape and our state. If you look at our state, we can actually adjust the local view size and increase this. And this will actually fill the local views, 5x5 views around its head. Plus, it will include the snake body, snake head, snake tail, and food. And we flatten the local view and add direction and food distance information to this, and we return the state. When we do that, we have to adjust our neural network size. Here in this case, we have a 5+5 grid, plus 2 for the direction and 2 for the food position. And as you can see, this is like a much simpler network. It only has the input, and then the 64 is its intermediate layer, and then the next layer is the action layer. So I guess the important thing here is that if you do change the state, which you can do by asking GPT or Claude, actually, it's very good at this, make sure to change the shape of your network to match the input size as well. And in the next one, we actually have, again, the local view size is 20, right? I just wanted to maybe encompass a 20 by 20 grid. And that's why when we look at the local view size, now we're getting 20 by 20 plus 2 and 2. So this would make our input size 404. So it's quite larger. And then you can train it like that. So the important thing is to make sure to match the input size to your state, which is what the model is observing. So I ran these with these two. These are slow learning processes, but feel free to experiment. I think you'll have the best luck with this simple implementation. But the exciting part is that make sure to change the state any way you like and see if you can get better performance. Thank you for watching. And as you may know, I actually offer consultations and one-on-one meetings at my Patreon. Feel free to check it out from the link in the description. So I do offer one-on-one meetings for higher level patrons. I hope you found this useful. Like I said, you can apply reinforcement learning to any domain in which you can simulate and you have clear actions possible. Let me know what you think, and I'll see you in the next video. I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects. As a patron, you will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses. And my most recent and most proud one, the 1000x MasterClass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well.